All right. And you got the output from it, Kapil?
Yes, I got the output.
Do you want to share your screen and walk us through what you've done?
Sure, sir.
Great. Let's see what Kapil has been able to accomplish. Hi. Manjunath? Oh, okay. Good to see you in person. I guess it's Manjunath because you're contemplating to come.
Can you see, sir?
Yeah. Yeah, we can see it. Yeah.
Okay. So I imputed the value after treating the outliers. First, I imputed before the treating outliers. I imputed with median. I didn't get good results. So after treating the outliers, then I imputed with the mean. I'll show you. Then also the results were not very good. Then I imputed with modes. So I got better results. And definitely after balancing the data.
Okay. Where have you done the hyperparameter optimization, Kapil?
Wait, sir. I'll show you.
All right.
Here.
But you're running on decision tree, right? You're not running on random forest.
Yes, sir. I tried this thing on decision tree only. Random forest, I didn't do the hyper.
Oh, okay. So then you're not able to get the output as well from the random forest.
नहीं तो उसमें I did. Wait, sir. I'll show you. Hyperparameter optimization means you're saying the estimators and all these settings, right, sir?
Yeah. So you have been able to run it. Yeah. So go down.
I've been able to run it, yes. But my
yeah,
estimators I've taken very less, 1, 10, and 100.
No, that's okay. That's okay. I mean, you still tried with the different settings over here. So I'll be curious to see what output you got from over here and how much time it took you to run this.
Around 2 hours.
Around 2 hours. So, folks, can we have the attention here? So we have Kapil who has been able to run the random forest. Kapil, go back to your hyperparameters settings like 3-4 lines earlier. Yeah. So these are the settings he tried: 1, 10, and 100 estimators, different depth. So you still tried like quite a few number of settings over here, right? And then you initialize that with respect to the balance data, right? Balance approach, and then you did the forest. Cross validation was 5-fold. Scoring was recall. Now come back to your results again. There you go. And you were able to get the recall of 77, which is pretty good actually. How much was the recall earlier on when we were doing the logistic, if you remember, of the tree for this data?
For tree, I got very good with hyperparameter.
45, 55 type of number, right? Yeah. So that's a big jump up in the recall value, and that's what you can see. I mean, it does have a benefit in sort of like running in the optimized fashion. And what is this one?
This one is after tree. Hyperparameters of optimization after tree.
After tree?
Yes, decision tree, sir.
Acha, this is decision tree. So you're saying decision tree is giving you better result than random forest?
After hyperparameter optimization of decision tree, I got these results.
Yeah, but still, like, I mean, you're saying that decision tree is giving you better results than the random forest.
I think the random forest, I need to run with more estimators, then probably I might get better results with random forest.
Got it. Manjunath, you had any luck? Like the one that he's looking at right now, 7491? Okay, yeah. So if you can also share what you've been able to accomplish, yeah, that'll be good. So I would recommend for the folks who were not able to get the output, try in a different way, right? So some of us were able to run and we got the output. So I'm not sure, whether it's a function of the system or the bandwidth and so on and so forth. Try that in the, and I'll show you the other one also, the H201. So hopefully that will accelerate the random forest fitting in terms of the hyperparameter optimization there, right? So we'll try some of those things as well. Cool. So that's good. Thanks for sharing, Kapil. And we'll wait for Manjunath to confirm whether you were able to get something. Otherwise, we will go on to the next topic. Yeah.
Okay.
Thank you, Kapil. And for the people who have not done the pre-reading, if you could just go to the blog, we will talk about a couple of brand new topics today, right? The first topic we're going to talk about is principal component analysis, right? And that is article number 36. So if you can go through it just as a high level view of what we do and how it works out. So you get the treatment like this, Manjunath, when you are here. Have it, no? She brought it all the way. So if you can go through it, folks, article number 36, and we will begin our first topic for the day, the new topic that means. Mhm. Okay. Recall for the class 191 or overall? Okay, got it. Great. So two people were able to get the results, Manjunath and Kapil. Others, you still have that as an assignment. Figure it out how to make it work, right? You can talk to these people. Not running. Acha. Then it becomes Yeah, definitely. Good to have you here. Acha. For 2 months, what? Okay. Huh. You've joined Walmart as a data scientist, staff data scientist. Okay, great. Congratulations. Yeah. Mm-hmm. Hmm. 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 Yeah. So you're just trying to answer that discussion point. Like, if building a model is that easy, then what do we do? The speed of the building and yeah, getting the data, all of that. Yeah, absolutely. So are you done reading the PCA or haven't started yet, or somewhere in between? In between. Okay. So let's see. Anyone who would like to share what is a PCA? Since you already done some bit of discussion on it earlier on in the previous class. I'll be back in a minute while you're reading. Yeah. All good. So this is first time, Manjunath, you're coming in the campus. You've been here earlier. Okay. Okay. I think I was there when. First day. Yeah, first day. Yeah. But first day there were a lot of people. They didn't join. No, those are actually all together. All together. Okay. Okay. Got it. Yeah. Yeah. Anyone has any thoughts? Anyone would like to explain what is a PCA?
Sir, I'd like to understand one thing here.
Just a second. Sorry, I mean, Manjunath in the class is speaking. So I know, I mean, you may not hear, so I'll just come
couldn't
to you.
hear.
Yeah.
Sorry.
Kapil, I'll come to you in a minute. Yeah. Go ahead, Manjunath. Yeah. Correct. Yeah. Go ahead, Kapil.
Sir, here we mean like the components. We mean that these are variables.
These are components defined from the variables. But even before we talk about what are the components, just what is the idea of a PCA is what we're actually sort of like, discussing as of now.
Right, sir. So this is basically to address the redundancy, right, sir?
Mm-hmm.
And basically the components that are resultant should explain around 80% of the original data variance.
Mm-hmm.
And what it says is PCA component should be more than equal to 1.
PCA component should be more than equal to 1. Okay. We'll talk about that. I mean, what is one we are looking at here, but carry on.
Well, this is what I could get from here.
Okay. Got it. Tanmoy? Yeah. Mm-hmm. Mm-hmm. Okay. Absolutely. Anyone else in the class? Yeah, Rashmi? Hmm. 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 Correct. Great. Yeah. Okay. Anyone else? Tejashwini, Pranesh, anything from your side? No? All good?
generator mode for the output. And there are several techniques of how we any PC which gets generated which has a value higher than 1 is something that we will use. Anything which is parallel to the accepted is something to get to know. So, and then we also go about doing rotation to prove the components. Then several other techniques. And then we again go ahead and plot a plot and y plot to check if there is any multiple linear. And if we have again go about doing. So when we also do this rotation, it basically helps us to get some very few important characteristics of it, like variance of rotation, and standard deviation, all of this should be understood. So further helps us to emphasize on what features are needed to get the right outcome.
Great. Yeah, I think, I mean, all of you have covered good pieces. Anyone else online who would like to explain what you understood from it? Folks online, anyone else who didn't get an opportunity to talk? Okay, so let me try to, summarize whatever all of you have collectively tried to explain. FM? Uh-huh. Less noise, yeah. Exactly. Yeah. Yeah, yeah, absolutely. So I'll just, without using any mathematics, folks, I'll just talk about the underlying concept, which I think you have already summarized, but just in case if anyone is not completely caught up, right? And let's see if the writing cooperates with me till how long. So first of all, you have to understand the concept of dimension, right? And dimension is nothing but your x1, x2, x3, like all, huh? Oh, my bad. Okay, sorry. Yeah, so these are nothing but your dimensions, right? And I think it was Tanmoy who talked about the curse of dimensionality as well, right? Curse of dimensionality means, I mean, as you have more number of dimensions, the requirement of the number of observations will be higher for you to build a good model. Otherwise, you will not get a good model, right? Good model meaning precision, recall, accuracy, MAP, whatever metrics you're looking at, right? And what it also means, if you have a high number of dimensions, so basically the problems which come in with the high dimensions are following. I'm just naming some of them, not necessarily all of them. Some of the problems are first is your curse of dimensionality, right? I mean that the data requirement goes higher, and you will not be able to build a model which will be having accurate value because you don't have enough observations. Curse of dimensionality, right? So that's one thing. The other one is you will have something called as a sparse matrix that Rashmi you talked about, right? So sparse matrix meaning that you'll have many values which are missing, right? And not necessarily populated. So how do you handle that as well, right? So that's the second sort of like, symptom that you're looking at with respect to high number of observations. The third one will be your linear regression problem of multicollinearity. And right now, you folks were struggling with random forest fitting because of that many variables, and it's taking such a long amount of time and all of that, right? So from the example that Manjunath was talking about, that what he's trying to do in Walmart, right? I mean, so okay, the model fitting time. If you have many observations, sorry, dimensions, model fitting time. And this HDMI cable thing just messes up the thing. I don't know why. The model fitting time will be significantly higher if you have the unnecessary dimensions. Right? When you're working with the baby data, who cares, right? I mean, 2 seconds here and there, who cares? But when you're looking at millions of observations and millions of columns, right? I mean, rows and columns, I mean, then this could be a game changer. So this could be a difference between the months of fitting the data and weeks of fitting the data, or weeks of fitting the data and days of fitting the data, right? So that's the difference that we're looking at in terms of some of these benefits, right? And then other aspects, Manjuna, that you touched upon is more in terms of you want to remove, I mean, if you have more dimensions, then what we call as you have more noise in the data. So if you reduce the dimension, you are denoising the system. I like that analogy that, you know, you have a particular FM band and so on and so forth. You can go slightly lower, slightly higher, all of that. But there is a point where you're not missing out anything and you're cutting out the noise. So that's also, you know, one of the things when you're actually reducing the dimensions, right? So what does it do without going into the mathematics too much? So basically, this is a tool for dimension reduction. So when you have a problem of too many dimensions, you can try dimension reduction, right? And this is a scientific way of doing that. So I'm just gonna bring out something. So I think this will be the same example that we will be looking at. So let's say I have variables x3 till x13. So I have 13 variables in my data, x1, x2, x3 till x13. This is my original data without dimension reduction, right? So then what will happen, and we will do this hands-on exercise, so we'll understand. So once we run through the PCA, which is nothing but underlying logic is singular value decomposition SVD algorithm. I'm not going to go there because that's too much technical, but it's basically does the matrix multiplication and the rotation in order to come out with the components like P1, P2, P3 till P13. So the number of components which will be generated by default will be exactly the same number of the number of variables. Then why is it called the dimension reduction? If I'm generating the same number of components as the same as the number of variables, then I'm not reducing anything, right? But what is the trick over here is then we will look at these components, and the way it is organized in the PCA is that this component has the most explaining power. So basically this component itself will be packing in the explaining power of, let's say, 3 variables by itself, right? So this principal component 1 will be a representative of the 3 variables that you have in your underlying model. Similarly, this component 2, principal component 2, may be representing 2 variables, right? And you will see we will generate the explained variance ratio. There's a metric called explained variance ratio, right? So you will see that principal component 1 might be explaining 35%, principal component 2 may be explaining 25%, then it keeps on going down. So then it might be 14% over here and so on and so forth. So basically, you don't have to select all the components. You have to select only that number of components which actually help you explain 80% of your underlying data, right? Some people use 90%, some people use other criteria, so we'll talk about that. So let's say I have 3 components. I'm just going to make up the number over here. So 30, 50, 60, 60 plus 14, 74, and then I'm going to grab one more. So now you can see principal component 1 explains 35%, 2 explains 25%, 3 explains 14%, and 4 explains 6%. So if I add up the explained variance, how much is it? Can anyone tell? That's 80%, right? So the crux of the principal component is that you had, let's do the before and after like they show in the advertisement, right? So before and after. So before you had 13 variables, now you have 4 variables. Before you were able to explain 100% of the data, now I'm able to explain 80% of the data. So I have only lost 20% of my original data's value by reducing the number of variables to almost 75%, 1/4, right? So the 75% reduction in the dimension I am only paying a price of losing 20% of my original data's explaining power. Not a bad trade-off, right? I mean, and you'll see sometimes this may actually result in a better model, that you are churning out the variables which are not necessarily required, and that basically helps you in terms of reducing the dimension, right? So I'll just recap everything for everyone. So we talked about the dimensions, which are nothing but the number of columns that you have. High dimensions may have problems like curse of dimensionality, that you need to have more observations to build a good model. You may have sparse metrics where most of the values are missing. You may have multicollinearity. We talked about one of the assumptions in a linear regression is that you don't have a multicollinearity. If you have a multicollinearity, then all the coefficients will be not reliable, right? We talked about the fitting time of the model, and the noise of the model will be higher in all of that, right? So the main logic over here is it will take the original number of variables, reduce that to a certain number of components, and those components will be a subset of the original number of data. So for example, we went from 13 to 4, a 75% reduction, close to 75% reduction in the number of variables, which will give us 80% of the data's original explaining power, right? So that's the crux of that. So I'm going to take a pause and see if there's any question, thoughts from anyone. Like, I mean, if somebody asks you to explain, you should be in a position to exactly repeat some of those things, is the intention. Any questions, doubts from anyone? All good? Okay. So before we go and do the principal component analysis, folks, I'm going to ask you to build a model, because I believe that we haven't built the multinomial model, right? So I'm going to ask you to build a model, and there's a rationale behind doing that. So we'll fit a model after doing the PCA. So I'm going to save all the burden for you. I'll share some of the code so that you can get started quickly. So this is the data that we're looking at. Have you worked with this data, people? Wine data? Huh? No, you haven't. Okay. So let's go ahead and look into this. So only this I'm going to give to you. The rest of the things I will ask you to do on the chat window, on the team chat window. If you can pull in this data and go to this link, which is there, UCI machine learning. And after you have read about this data, tell me what this data has actually. And what are we trying to do? So the idea over here, what are we going to do is, I will show you the difference. So we're going to build a random forest without optimization. We'll just do the balance, right? So we'll do a random forest. Without the PCA, without PCA, and then we will do with PCA. And we will compare two things. And you can do your hyperparameter optimization if you like. We'll compare two things. The model fitting time and the model's performance. These are the two things we will try. Right, so I'm going to give you the end-to-end walkthrough of how you would put PCA to work. So one model we're going to fit, which I'm asking you to do right now, without PCA, build a random forest to predict something in this data. So after you read about this data, let me know what is it that we are predicting. And what this data has. A lot of people use this data. Others may not know. So just go to the UCI machine learning link and let me know what you think it is.
139, open this. I want to see why Nmat is saying this as open.
It is unmuted, I believe.
Okay. So this reason.
And kindly confirm once you have imported the data and you're good to go. Because there's fair bit of typing over here, and if you mess up the name, then it may not come out correctly. That's why I shared this data with you. First and second line I've shared with you only. Rujul, can you send on the WhatsApp as well?
Yes, sir. I'll send it on WhatsApp as well, sir.
Some of the people are not there, but they have the WhatsApp on.
I'm sorry. Hi, Ratnakar. Actually, I'm trying to open the link, and just a while ago, I see that another link has been shared. So I have opened the second one. Which one should I open here? The UCI page?
I'll share that link. If you just click on that, so for example, you can see my screen, right?
Yeah, I do see. I do see that.
So Zara, if you click on this link, hopefully that will take you to the right place.
No, it's not. It's coming not found.
Okay, that's fine. So I will just remove this. There you go, right? So just remove the last forward slash.
Okay.
And look into this data, right? And you can also sort of like, just go and say UCI machine learning wine. And there are many wine data. So just make sure that we're looking at the right one, right? So wine data set, for example, this one, it will take you there. And it'll talk about some of the main things. So 178 observations, 13 rows. Let's see how much we have in our data. I believe it's the same thing. 178 observations and 14. So I think they are talking about the columns separately, if I understand correctly. Alcohol, malic acid. Yeah, so they're not talking about the class of the wine. That is different, right? So this is the data, right? I mean, so just I'll paste this link for you. Where? Yeah, wine.data. You're importing the file, huh? No, just run this code. It should directly be fetched. So like you just passing on this entire link, right? This entire link you're passing on, and it will be read from there and will be saved in the data frame called wine. You don't have to download that. You can directly read from there. Unless you want to download and then explore. Hmm? Correct. 178, 14 is what you should be getting. So once you've done the step 1 and step 2, just go along with this and you can do just do some quick descriptive. You don't have to necessarily follow all of this that I have done over here, but do a class label size as well. So wine group by class label and then do a size, or you can do a value count, whatever, right? And there are 3 different classes, first, second, and third. And there are number of wines that are there, number of samples which are there for wines, 59, 71, and 48. Make sure that you're able to replicate this output. That is there in the the link UCI machine learning. So just take a look at what these variables really mean. Yeah. Sorry. You have intelligence is there. Yeah. Sometimes it works. Sometimes it doesn't work. I mean that's the thing. Extreme. Huh? You have to do the random forest after the scaling and everything. So people who are done, you can move on with the random forest and we'll talk about the data as well, what this data has. So fit it on the X train and Y train and then make the prediction on the test. Uh, find this. You done? 94. Okay. Great. We'll wait for others to also confirm. And you have done the grid switch. For the random forest, right? You have used what? Weighted average? Or you're not getting that error? Weighted average you've used. No, no. So I'm getting this error. Just a second. So I believe we have to, in the scoring, we have to pass on that we are looking at either micro, macro, or weighted. Accuracy, not the recall. That's what I'm trying to fix. That's okay. I'll just try this one. Hmm? Ah, okay. Mm-hmm. Build a random forest model with the hyperparameter optimization. Sorry. Hmm. Tell me.
Sir, I'm also getting the error. One or more of the test scores are non-finite.
Sorry, say it again.
One of the more test scores are non-finite. I'm getting that error. And if I try to get the best score, it is NaN.
Yeah, so that means there might be some missing values somewhere. Something might have happened.
Okay.
It's not there. Oh. So NaN generally means, something might be going on from that point of view. So just take a look. Otherwise, you can share your screen. We can then analyze.
Okay, let me check.
Is it? I'm trying to fix it. Let's see if it works. Yeah. Let's see if it works. I think it's doing something. Try to run it again, Bhavna, like all of them. One more time, see whether that fixes the error or not.
Okay.
Bhavna, is your problem fixed or you're still facing the same challenge?
It's still running. I've executed again.
Okay.
But there were no missing values.
Hmm. It is taking time for me. So 7 minutes plus running. How much time it took for you? 10 minutes only. Okay, okay, got it. Yeah. I don't know. I mean, it's doing something, so I'll just wait for it. Yeah. How much time it took you for? Huh. Huh. That you're using the average. Correct. So the reason why that is the case is because you have to pass on this parameter as well. But that's what I'm doing actually right now, because it's a multinomial classification, right? So you have to pass on another one of the hyperparameters, which is the scorer. So sklearn.metrics makes scorer, and sklearn.metrics recall score basically, and average is weighted. So if you don't do this, then it will throw that warning and then the numbers will not be generated. So the average is weighted over here. That's what I'm actually trying to run. And then once you do it, then you will pass it on as a scoring equal to that parameter, right? So you can try that with that setting. Which one? So you have to create the scoring one, then it will work. But it's just taking very long time for me also. Normally it doesn't take this long, even though it's a very small data. So I think it'll be a good thing for the PCA to prove. Try it out. Let's see if anyone is able to get it faster. Or did it come back? I think it may have. Yeah, it has run. So it took me 573 seconds to fit this model. I haven't done any diagnostics on him, but just let's make sure that you have the model output. 573 seconds. And also insert these two lines, people. So import time and then set the start of the time when you are fitting the model and running it. Ideally, you should do it right over here, but it's okay. I mean, creating the instant doesn't take very long time. Start time. And then once we are ended, that is the end time. And then we're gonna print the time it took us to get the output, which is 573 seconds for me. Where? Correct. Yeah, correct. Yeah. And yeah, because this was the one that was giving you the error, right? Sorry. Hmm. Oh, where we are using it, I'll show you. Scoring is equal to scorer. Scoring is a parameter there. How do you want to score your model? 89. Let's see what else people get. How much time it took for you, folks, to fit the model? Hmm? Time, yeah. So you can time also, folks, using this. So like the start time is time.time when you actually fitting the model. And then end time is when the model has completed fitting the model. And then you're going to take a difference of these two to get the time that it took for you to fit the model, which was in my case coming out to be 573 seconds. I'll share this code on the chat also in case if you're wondering. You can time the fitting of the model. Hmm? Just a second. Sorry, you're saying something? It is? It is reduced, yeah. But not that much, huh? The accuracy. But the time would have come down. Or the recall, you're saying. Okay, got it. We'll discuss. Actual 6. Actual 6. Okay. Actual 2. 20. Correct. Ten. 26. You can also do this confusion matrix for the 3 classes. Yeah? Small, small. Is everyone done? Or are you still working on it? Working on it? Oh, fair enough. Folks online, Bhavna, are you sorted out or still having challenges? What is the password? Rashmi, do you remember the password for Viva? Same password. Yeah, coming just a second. Let me just set up this one very quickly. Tell me. What's going on? You done? Yeah. All this stuff. For the PCA. So, without? 721. And the model performance? Shall we do a quick walkthrough, people? If you're still working on it, or you're done? You done? Yeah. Timing is the same. Okay, shall we do a quick walkthrough, people? Or you need some more time? Folks online? Yoshini Tanmoy, you still working, or shall we do a? You haven't done? No, PC, no. I mean, I'm not talking about the PC. I'm saying just the normal random forest model. Okay, then let's just go through and let's make sure that you are everybody's on the same page. So we have done the interactive cell. We imported the wine data set. What is the wine data set? Anyone? It's a wine tasting club, right? And they've been asked to sort of bucketize the wine in the three categories, 1, 2, and 3. And then there are underlying characteristics of the wine, such as alcohol. What does it mean? Percent alcohol, right? So is it 10% alcohol or 15% alcohol or whatever that number is, right? So that's the alcohol. Similarly, there is a malic acid, ash, all the things are there, right? Flavonoids and stuff like that. So these are the characteristics of the wine and how dark and so on and so forth it is, right? So these are the characteristics, right? And these are the three classes, first, second, and third, right? So whatever that rating really means. I mean, there are 59 wines of the class 1, 71 of class 2, and 48 of class 3. Everybody's clear so far? Yeah. And then over here, we've done the average, right? So class 1, for example, you can see alcohol is 13.74. Class 2 alcohol is 12.28. Class 3 alcohol is 13.15, and so on and so forth. So you can see there are some differences in the wine depending on the underlying parameters that we're looking at, right? We did an info. There was no missing value and there was no categorical value. So we were good to go with the modeling. Correct, everyone? Then the next thing we did was to separate the X and Y. X and Y were separated. Normally I don't do it, but I think, I mean, might be for some reasons, I mean, I have used the capital X, right? So separate the X and Y, and then we did the scaling. From sklearn pre-processing import scale, and we did the scaling of the data, right? And post scaling, you can see every parameters, and we only scale the X, right? So that's why we actually separated the X and Y separately. Post scaling, and for PC also you need to do the scaling, otherwise it won't work accurately, right? And we did the scaling, and you can see the minimum for each one of them is 0, and the max for each one of them is, sorry, what scaling we have done here? Just a second. Oh, I think we've done the standard scaling here. Yeah, we have done the standard scaling over here. So scale is basically not the min-max scale, but the scale, which is the standard scaling. So you can see the mean is 0 and standard deviation is 1. What does the standard scaling mean? Anyone? Okay. So we talked about the min-max scaling last time. So in this one, we've done the standard scaling, which is nothing but the computation of the z-score. And what is a z-score? Correct. X minus mu divided by the standard deviation. So for each of the observations, we will compute the mean, standard deviation. From the individual values, we will subtract the mean, divide that by 1, right? So that basically computes the z-score. But the standard normal distribution is a distribution where this mean will be set to 0 and standard deviation will be set to 1, right? So that's the standard normal distribution, right? So over here, which is something like a z-score computation as well. So over here, you can see that mean has been set to 0. Like, I mean, these are all negative values, big negative values, right? So there's 0, e to the power minus 16 basically. And then standard deviation for each one of them is 1, right? So this is the standard scaling that we've done. Then we're going to do the train test split, all the regular flow. And then we have done this is new, which is the sklearn metrics, make scorer. And we're going to have the recall score and average as the weighted. Why are we doing this? Anyone? Because we are getting the errors, right? Yeah, it was giving you the error that the average is not defined for non-binary classes, and you have 3 different classes. So consider using the weighted or something of that nature. So because the multinomial classification that we're doing, that's why we're actually doing it, right? So that's why we are saying, do not do the average weighting, but look at the weighted average. Everybody remembers the weighted average concept? I asked a puzzle question like, I mean, the product A profit margin is going higher, product B profit margin is going higher. Can it be possible that the overall portfolio is going down? Yes, it indeed possible. That's the weighted average, right? So it's doing the weighted average of that, right? And then we have the balanced and this, right? And then we import the grid search. Over here, we begin the wall time. So it will say, you know, when exactly in the system I come to this stage, and it will store that value in the start. And then it will go through, create the instant of the model, and I'm doing a 4-fold cross validation and all of that. And then we will fit the model, and then I'll say end time. So it will say what time I actually came to this particular part of the code. And the difference between the start time and the end time will be the training time of this model, which in my case came out to be 573 seconds for this random forest, right? And then we go through the regular drill, like the best parameters. What were the best parameters that came out? What was the best score that came out? And then what was the feature importance? And let's do this also. I think last time I said, I mean, we will do it in next class, which is the plotting of the feature importance. So I'll give you time to make sure that you've done this step as well. So what is the most important feature in doing the classification of the wine? It's this guy, proline. Proline is the most important variable to separate the wines categories. The next one is a flavonoid. Huh? You got different one. Huh. Hmm. Hmm. Proline is coming in. Color intensity is here as well. Yeah, that's the fourth most important feature, right? Alcohol. So I mean, these are your top 5 variables: 1, 2, 3, 4, 5. And this is the code how we got it, right? So basically, you have the estimator feature importance, you have the index, then I'm gonna do the sort values, and then we will do the bar plot. We will rotate the axis to 90 degrees so you can see it, and then we're gonna display that. Rashmi, Pranesh, you have this chart, or are you working on it? You working on it? Okay, fair enough.
Decision regarding that. And then your decision will be what is not now we take the for and here it was still ID, but still it would not be right because exactly.
This is the parameter for the random forest. If you pass on anything over there, that by default that will take only that many parameters. So rather than 10 feet, so by default that will take 10 feet. Right? So it won't be optimized. Already specified.
But I think what now this is what whether you want it here or here, it will still not connect to this. It would connect to my tree.
It will not connect because this is the instinct that we're using. So there's a picture that I'm going to do. You know, because like the entire rest of the random forest. We don't take it. Because it's good that you take it. I'm just not taking it.
Now I just change.
It's going to take some time. That's actually
To make it work.
Folks online, anyone who needs any help? Okay, I take it as a no. So let's do the feature importance very quickly, and you'll see something like this coming up, right? After fitting the model, you can do this. Correct. So in this case, Proline flavonoids, this variable, color intensity, alcohol. These are the top 5 variables. So you're right now here, Tejashri. So once you do it, then you can move on to the. You are not doing the timing also. Are you doing the timing? You're doing the timing? Okay. So timing and then best parameters, best score, and then you can just go down to this line, which is going to give you the feature importance in the descending order. Not yet, not yet. You just doing still like random order. Because I realized that we haven't done a multinomial, so I just want to touch base on it. Underscore, yeah. But you're I should do something not aware of that. Like when you generate like it will generate like details. And when other algorithms that is there, not sure that there might be some option like verbose or something. Correct. Correct. So it should be that. Just do a quick look like how. I think verbose or something like that one. Sorry, I think so. No, it's actually not working. Sorry. Guest or staff, which will select next? Separate. That's right. Very good. That's the perfect. Yeah. The integration or the missing method or the mean or median. Can you do it differently or will you get the entire set and do that or will you do on the training set for the No, for the entire set. Because you're going to predict on that data also, right? So if there's anything missing, then it won't be able to make the prediction. Can you do it in a different way? Because if we see, because when we do integration of the median or mean, I'm seeing the entire data set of the test data set as well. So I should not be seeing the test data set because it won't be. Otherwise, the data leakage kind of thing. No, but when you're building a model, you have to do on the test. Na? Otherwise, how will it handle the missing value? No, test data will do differently. Might be on the test data set, we do separately. The training will do integration. No, when you develop a model and you are gonna deploy that model, let's say there is a missing value coming in the live data. So your missing value strategy will remain constant with respect to how you have developed that model. So you should do the treatment for the entire group for the missing value. Sorry, I'm not following the question. You're saying, I mean, like you should not do the missing value for the test data. Test data might be in the test data set, whatever the information we have. It won't work. SQL and predict will not work. It will say I have found NANs. I found missing values. If you impute in a certain way for your training data, impute in a different way for your test data, that will affect your results. You can try it out. Are we good with the feature importance? Still learning, acha. After the fishing, sorry. After the feature importance, let's go ahead and generate this confusion matrix. So you can start typing this code also. 1, 2, 3, confusion matrix. Now we have 3 classes. So I'll ask you to predict, or I mean, tell me what exactly this really means. Huh? 97, 1 and 1. Okay. In this grid. Okay. Yeah. Got it. Okay. Got it. So who would like to interpret this classification report? If you have the output, anyone online first? I believe everyone has the classification output, right? Or no? Bhavna, Kapil, what do you think? Gerard?
I have the output.
Yeah, you good? Okay. Yeah, so anyone who would like to interpret this? How do I read 0.95? 0.95. 0.95, this number right here. Mhm.
It's the detection rate, right, sir?
Yeah, that's correct, Kapil. So build more on it.
So this is that 95% are detected correctly
95% of what?
of class 2.
Correct. That's correct. Yeah. So 95% of class 2 wines were correctly, or I mean, was detected by my model, right? What
Yes.
do these numbers mean? 10, 20, and 6. Correct. Support.
Those are the number of wines.
Say it louder, Bhavna.
Those are the number of wines present in class 1, class 2, and class 3.
That is correct. So there are there are 6 wines of class 3. There are 20 wines of class 2. There's 10 wines of class 1. That's correct, right? And then you have all the other things that you're looking at. So my test data has overall 36 observations, which are basically, these are the breakup of the wines, right? Now I'm going to do a classification report on this. And remember, this is a multinomial model. So you can see now we have 3 by 3 matrix instead of 2 by 2. So it's not always the 2 by 2 that you have to look at. I mean, sometimes it could be 3 by 3 also. That's what we are looking at. So go ahead and take a look at this, and you can see that there is only one wine which is misclassified. And which wine is misclassified? Who can tell? 2, correct? Yeah. Actual was 2, and what was the predicted?
1. It was predicted.
Predicted was 1, right? So one wine which was of the class 2 variety. So again, you can look at these. So actual class 1 were 10 wines. You can see 10 wines are here. Actual class 2 were 19 plus 1, 20 wines, which are here. Actual class 3 were 6 wines, which is here, right? So now if it is all on the diagonal, that means it's a 100% correct classification, right? So, but there is one which is over here. The actual was 2, but the model predicted it to be 1. So this is the misclassification, right? And annotation, you could actually make it more fancy, I mean, whatever you want to do. So I'm going to do the red, yellow, green as well.
सर वो रेड येलो ग्रीन का सीक्वेंस चेंज करोगे ना तो आएगा.
Oh, my bad. I'm putting it in the wrong one. That's why it was not working. So CMAP is the one that we should be putting. So I just confused where are we putting it. So this should work. There you go. Right. Or you can have greens or green. Let's see whether the greens work or not. Green also work, right? So whatever makes sense. That is what we should be looking at. So this is a wrap of a multinomial classification. Now, shall we move on to PCA, folks, or are you still working on it? Tejashri, Tanmoy, still going through? Okay. Rashmi, Pranesh, you good? For the confusion matrix? Huh? Okay, sure. You're good, right? Manjunath is good. Folks online, if you're not done the confusion matrix, you can take time to type it out.
I have completed till conclusion matrix.
Say it again, Bhavna.
I have completed till the conclusion matrix.
Okay, awesome. Sorry. हाँ हाँ ठीक है करता हूँ फोन चल That's a good thing. हैं? Sorry? Yeah. Uh-huh. On the X test. Yeah. Predicted is coming in from here. No, no, no. Should be for the X test. Here, this one. Only for the test. Is everyone done with the confusion matrix? Yeah. Still working on it. Huh? Sorry. Huh. Why? You're doing some new data. Huh. Oh. No, scale only X, but do for both train and test. So you never scale Y. You will do the scaling of X only, but for both. Correct. Correct. Not just the train, because then you're fitting model on only on the train. That won't work. That won't work. That won't work. Both of them. So maybe 5 more minutes for you. Folks who are done, then you can move on to like execution of this PCA. So just to go ahead and start typing this code, and I'll come back and explain what we're doing. So start writing from this line onwards, where you see on my screen. We're done with all the previous steps on this. We are supporting customer service. Customer service. They call the NFP. Yeah, computer is also there, but mostly NFP. Because the content can be transcribed. So I'm talking that can be transcribed. Right. How many years? And your friends are in the same experience. They are both in the analytics. I'm here. Now you have a Walmart, right? Well, wherever you are in the entire industry, is so much around. Right? Are you sorted? Oops, just read. Shall we move forward? All good? Okay, great. Now we're gonna go to the PCA, right? So let's start executing PCA. So from sklearn.decomposition, import PCA. I think some of you have already done it. So if you have done it, then it's all right. And remember, so we are doing similar way like we have done the previous ones, right? Which is first importing, then creating the instant, and then fitting on the scale data. We never scale the Y variable. Only, we never do the PC on the Y variable, only on the X, right? So that's what we are doing, which is we are doing the PCA on the X scaled. And when you do the PCA, it will say, yeah, that's fine. We haven't passed on anything. And then this is where we see the explained variance ratio. So I'll just give you time till line 99, 100, 101, right? So we just imported the PCA, fitted the data on the scaled, And then we said, okay, go ahead and show me the explained variance ratio. So what do you think are the number of entries over here? Same, right? What is the error? Does anyone remember? That's fine. Shape. I'm just gonna do the count, right? So if you look into this explained variance ratio, so this gives you the explaining power of the original data, right? So what does it mean? So there are basically, so let me first show you that there are 13 components in this, right? Why 13 components? 13 number of features, right? And then we will come back to the explained variance ratio. Who would like to explain this line? Anyone? What is the output telling me? It's already sorted. Already sorted, but what you can do is you can just reduce the decimal. Three. Oh. Now, what does it mean?
So here component 1 explains 36% of data.
That's correct. That's correct, Kapil. So the principal component 1 has original data's 36% explaining power. Principal component 2 has 19% of the original data's explaining power, and so on and so forth, right? So you can see that as the number of components go higher, I mean, or as you go to the higher number of components, their explaining power goes down and down and down, right? Right. So the general rule of thumb that we use is the number of components which explain 80% of the original data's variation, right? So let's see what that turns out to be. So 1, 2, 3, 4, 5. So if you do with 5 components and then do a summation, you can see it's 80%, right? Because I just said, okay, are these 5 count up to this, right? So then I'm gonna do another PCA and I'm saying this time do a PCA with only 5 components. I don't want to have all the components, but I just want the 5 components there, right? So remember the first one that we created over here, we did not pass on the parameters like how many components that we really want. In this one, we are saying we want only 5 components, correct? And that's how basically we are able to do. And this explains the 80% of the overall data variation. And then we get this Also, which is very different from what we said explained variance ratio, this is what we call as an eigenvalue. An eigenvalue is basically 4.7 variable worth of information is hidden in this component. 2.5 variable worth of information is hidden here. 1.4, 0.92. So if I followed the eigenvalue math, I would have dropped these variables or these components, because one of the rule of thumb that you saw over here is that eigenvalue for each of the components should be more than one. But the reason why we are not dropping is because I want to get to the 80% of the explanation, which is what I use actually, minimum 80% of the explanation. Yeah. So this is the overall variables worth of explaining power, right? So we use this to pick the number of components so that we get 80% data's explaining power. Correct? This point is clear. Other rule of thumb that people use is eigenvalue for each of the components which is selected should be more than one. So at least eigenvalue is nothing but how many variables worth of explaining power I'm packing. So 4.7 means that this component is equal to 4.7 variables in the original data. This component is worth 2.5 variables in the original data, right? So like that. So another rule of thumb says that don't pick any web component which doesn't even have one variable's worth of explaining power, right? But I'm overruling that. Why? Because we want to get to the 80% of the explanation of the original data, correct? So that's the reason. So now, after we have done the PC again, we will create this, and this is what the PCs look like. So I will wait for you to confirm whether everybody has done this output, and then can anyone tell me what this might really be, just based on your intuition? Which one? This line here? Right. Anyone needs any help, or we're good? No. PCA you're doing for the entire X data. Entire X data. X. So you had your original data. You created the features and the labels. Then you scaled your data. Features was scaled. Once you've done the scaling of the features, then you will do the PCA. And then you will break your data. Now we will break the data, yeah. I'll walk you through those steps. So your data will be shrunk actually. So instead of 13 columns. Yeah. So it will be now 5. Instead of 13 columns, it will be 5 columns. 5. Yeah. Yeah, we'll get to that stage. Hold on to that thought. Yeah, Tejashni, any question? Achha. So everybody's till this stage all good? So, you can see the reason why we chose 5 components is because I wanted to get to the 80% explaining, right? And that's what we have done. And then we are moving forward and we did this, which is the PCA. PCA is the PCA with 5 components. And then I'm saying X dot columns. So you can see these are my components. Component 1, 2, 3, 4, 5. These are what my 5 components look like, right? If I do 6, just to really show you that, this is how it really works out. So let's say for whatever reasons, I wanted to have 6 components, right? Now you will have 6 components. 1, 2, 3, 4, 5, 6. Everybody's clear on this part? You want to do 7 components. So 6 components explain 85%. Let's say I want to do 7 components. I want to say, no, my business is asking me to do at least 90% in my components, right? So it may be driven by that thing. So let's do 90%. So 7 components will give you close to 90%, right? And then these are my 7 components. 1, 2, 3, 4, 5, 6, 7. Right? Everybody's clear what these values are? Now, what do I do with this? You don't have to worry about anything, but I just wanted to show you what is a component. So component 1, for example, which is the Python index 0, is nothing but 0.144 times alcohol minus 0.24 times malic acid minus 0.00 times ash and so on and so forth, like a linear regression, right? So it's a linear combination of all the original variables that you're looking at. So component 1 can be represented by 0.4 times alcohol, 0.24 times malic acid, 0.00 times ash, 0.23 times alkalinity of the ash, and so on and so forth. What is component 2? Component 2 is 0.48 times alcohol, 0.22 times malic acid, and so on and so forth. I hope this is clear, concept-wise, right? And this will give you the loading of those components. So for example, you can see component 2 is a very, very good proxy for alcohol. So it's capturing the alcohol dimension of the original data. Component 1, what is the highest loading you see over here? Biggest value basically. Phenols, and then this guy over here, proline and all of that, right? So you can see if I were to pick one, phenols are represented in component 1, and you can see these are absolutely not there in the same quantity in any of the other components. So phenols representative is component 1. That's how they are actually capturing the original data's value, right? Alcohol loading is highest over here, right? You can see none of the other components had that high the alcohol loading. So component 2 is actually a proxy for alcohol for a large extent. We'll do a heat map as well, but it doesn't matter. That means it's like the loading either positive or negative. Yeah. Correct. Each component will be a linear combination of original variables, but depending on the coefficient, it will be over-indexed on one variable or two variables. So for example, component 1 is over-indexed on, like we were looking at this, the highest values phenols, right? And then these two guys. So it's basically loaded on phenols and diluted wines and proline. Component 2 is heavily loaded on alcohol. I can tell from the number that we're looking at, and up to a certain extent, proline and all of that, right? But oh, sorry, color intensity is also very, very important for component 2. So that's how basically they try to capture the original data as well. So those variables are gone. If you run with this data, those variables are gone. Now, instead of those variables, you'll have 6 columns. So those 13 columns are replaced by 6 components in your data. And each component is a mathematical derivation of the original variables, which is I'm showing you. You're not seeing 13 columns. You're saying components. I'll show you. I mean, so let me just actually walk you through. First of all, I'm going to show you the correlation heat map. Well, is that correct? PCADF shouldn't be supposed to be like that. Hold on, let me just remove some of this so that, I mean, we're looking at a more reasonable one. PCA, that's fine. Okay, never mind. I'm looking at the loading. Okay, that makes sense. Yeah. So I'm going to show you this thing actually. So it's called PCADF. So PCA underscore DF dot core. Somehow I lost the connection. Yeah. No. Okay. So I'm still not there yet. So that's why it is coming like that, right? Okay. Hold on with that thought. So let me just give you a walkthrough first, right? Before I talk about the point that Pranesh you're asking. I mean, hopefully that will be answered there. So I'm just gonna take. So let me remove this over here. Right, so this is clear. Now what we're gonna do is we will just import NumPy pandas, all of that, PyPlot, pandas profiling. I mean, not needed. But what we're gonna do is we will do the heat map of this chart that you saw, which is a pictorial representation. So you can see visually, the component 2 is loaded more on alcohol and color intensity, as you talked about. Component 1 is loaded more on phenols that we talked about, right? Similarly, you can see, there are different things which are peaking actually, right? So it's sort of like, gives you a visual of, what are the loadings, right? Let's move forward. So original data shape was what? 178.13. Now I'm coming to a point that you're asking. 178.13. So I've formed 5 components. Now I will do fit transform, which is now you're converting your original data. Till now you've just done the PCA. It remembers what PCA you have done. I'm saying now go back to that PCA and transform my original scaled variables, right, into that. And once I do that, you will see now I have transformed this into this variable called as X scale transform. And then we're going to do the X scale transform, and I will add the column information because it's nothing but if I just show you a, huh? Correct. So if I show you the shape of this person, you'll see it's 178.5. Why 5? Because those 13 variables have been taken out and they have been replaced with these 5 components. Nothing changes in your rows. All the original rows remain as it is, but those 13 variables have been replaced by 5 columns, right? And now what your data looks like is this. Your data doesn't have the x1, x2, x3, x4. Your data has p1, p2, p3, p4, right? So these are the components, and this will now go in the model. Now you have to do the train and test split on this, rerun the entire algorithm, evaluate the efficacy of your model, the time it takes, and all of that. Now, if you're not doing this with the 5, and I'm just going to show you so that you become clear on this. Let's say I'm going to do with 7. Okay. So I have to fix this also because now it's saying you need to label more. Now your data looks like this. Everybody's clear on this part? Manjunath, you have some. So 3.31, this value for the row, for that particular row, so for that particular row, grab the value of alcohol, grab the value of malic acid, grab the value of ash, do this math, you will come out with 3.31. So your original, correct, yeah. So original values, your principal component 1 is nothing but a combination of these, right? So for that original value in your 13 columns, what were the values of all of these variables? And then you have to multiply with these coefficients to get that, right? I'm not going to ask you any mathematical questions on in the exam, but you understand the concepts on it, right? I mean, how does it really work out? So that's how it is, right? So these are the components now. 7 components I have. Now with the 7 components, we are getting how much explaining power? 89% of the original data's explaining power, right? I'm going to go back and revert back to 5 only, right? Because that will be much more faster algorithm in my view, and you wouldn't lose a lot of information. So I'm just going to go back and do 5. And then run it, and then just go over here and say run after. I mean, there's a shortcut as well. Now it's gonna again throw me an error. You're passing on too many. Oops, sorry, yeah. One day. There you go. So this is the entire piece you worked through. Right? Now I know it's 1:35. What time you want to head out for lunch before we build the model? You want to go now? So after we come back, we'll build a model on this again with the random forest. And then we will shift gears, and I will ask you to do the PCA on your loan data and see whether then you can fit a random forest as a homework. Not now, as a homework you can do that. But then after that, we'll shift gears and talk about the market basket analysis after we finish this entire exercise. MBA. That's the flow. H2 also I can bring up today only. Let's see. I mean, I have one more class, no? No, 5 classes I have. 5. I think after this, one more. That's the last one. Yeah, so I will definitely bring in H2O in the last one. Which one? This one? Oh, fair enough. So exam will be mostly hands-on. I'm not going to ask you theoretical question. I'll maybe give you a brand new data set in a timed fashion. You have to do certain things and report with your insights. So if you're just doing things here, then you don't have to prepare for the exam. Of course, you have to understand what you're doing. So you can copy, open book. Copy from wherever you want to copy. Yeah, that is the reason.
You have 2 sessions, section A, section B.
Hmm.
Entire video. We don't even have time to give them.
Which module was it? Which subject?
Applied statistics.
Applied statistics. Dr. Simas or Mithun? Okay, okay. Acha. Well, I'll size it up. I won't overload you with a lot of things, right? So
No, honestly, we did not have that much of time. We also what went with here.
Mithun might be testing your stress level actually. Rather than the statistics, he might be just testing how you do managing the work pressure.
I was thinking,
I will give you a baby data, but I mean, and in most of my exams and assignments, I mean, you wouldn't see a huge distribution. Like, I mean, it's not like if somebody gets 30% or another person gets 100%, right? I don't do that, right? But if you totally suck in your code and you're not able to run that, right, then you will not get more than 50%. So that will be the flow. Hi, Shinu. Yeah, yeah. They were just talking about the exam and how many classes and all of those things. They start worrying about the exam the moment I say one more class. Okay, talk about the exam first.
the exam means my years also.
So we have one more, right? I mean, this is 5 classes. Yeah.
No. You can't get a better jokes about it. Two things. My Bible is fun, asking also.
I try to lighten it up. Yeah. Don't overload them with the intellectual burden.
But otherwise, I think we did not get much to talk about it. And then exam really happened on the day of exam and we were big holiday. But now I think we're getting a lot of.
Great. So people who are done with the code, you can proceed for lunch. Up to you.
Sir, can we have the lunch break till 2:25?
Sorry, say it again.
Sir, can we have lunch break till 2:25 p.m.?
You saying you want to do it 2:25 or till 2:25?
Yeah, till 2:25.
He wanted till 2:25.
Till 2:25. Yeah, that's fine. That's fine.
Just share the screen and get permission.
Yeah. Shinu's here and Shinu decides what gets done, right? Share your screen, show that you're done, then you can proceed for lunch. Manju has taken a leap of faith. He came from online to offline. Acha. Okay. At least for my class first time, yeah. So, yeah. Kapil is online. I'm not sure. Kapil, where are you from?
I'm from Delhi.
Okay. So you're planning to come down and say hi sometime?
I will plan to